Hi everyone, I am Tahir. I am a PhD student in the Department of Computer Science, and I, along with my team, we have been working on this IndicWav2Vec model, which is a Wave2Vec implementation of for the Indian languages. So it is basically, it constitutes of around 40 Indian languages. I mean, it's trained on around 40 Indian languages. So the multilinguality of it is, it's of great use. So I'll be talking for about 15 minutes, just going through the model, seeing what its details are, so that it becomes easy for you to grab things in the hands-on session. And similarly, my other colleagues, my other teammates, they'll be taking 15 minutes to finish off these presentations. So we will start quickly. So yeah, so just for the sake of completeness, what ASR means is simply is you have an audio waveform and you have a system. The system takes in the audio waveform as input and just transcribes it in its native language, whatever the case is. For example, a Hindi audio would be just transcribed into the Hindi characters. Now, what the problem with Indian languages is, so we have these ASR systems, as I said. So these ASR systems are good for English. Why? Because we have the data and everything there, right? So we have tons of data. We have thousands of hours of data available for English. But for Indian languages, this part is particularly missing, right? We don't have this labeled data set there, right? We don't get it right on the internet, right? So that is the first problem. The second thing is, even though there are some models which are available in Indian languages, for example, Google does host some of these models, but the problem is that those are closed source, right? We don't have access to the model, right? So some way or the other, it's a breach to privacy. I mean, we don't know how our data is being used. So for someone who is very specific about this privacy thing, so he may not choose to use these systems, right? So this open source thing, right, is not present for these Indian languages at all. And our focus at AFR Bharat is we want to open source all the technologies that we make, right? And the third problem with these Indian languages is that we have this rich inflectional culture in Indian languages. So that asks us to build a good language models for these particular languages, which we are again missing just because of lack of data. So I'll just quickly go through this traditional ASR systems, how traditionally this ASR used to be modeled, these ASR problems used to be modeled. So there used to be a separate set of components. For example, this feature extractor part, right? It would take your audio as input and extract some useful features from it. The second part is your acoustic model, which would kind of model your phoneme probabilities. Your pronunciation model, which would just then take those phonemes and just output your characters. And then a language model, which would just kind of rescore those outputs to give you a better output from the model, right? But as you see that there are a few components involved in it, and inefficiency in any component can lead to the whole pipeline being useless. So you won't be able to get the desired output if one of the component is problematic, right? And the second obvious thing that comes to mind is that the deployment would definitely be difficult for such models, because you have to kind of take care of individual component and then just couple it in the right way. And also the main problem there is that you don't have any provision of using unlabeled data set, right? Which is very, I'm just highlighting the word unlabeled, so that will come in the picture right in a while. So the problem is that for training these models, you should be having a labeled data set, because the unlabeled data, it can't make use of anything, right? And so the question is, can we do better, right? So as Pratyush sir mentioned that the new trend of models that are kind of ruling over the market now are these end-to-end based models, right? Where you have a single function, where your model learns a single objective function and learns it from end to end, from feature extraction to the output generation, right? So all is taken care by a single model pipeline. And the second important thing that I was telling about is that curation of this availability of this unlabeled data, right? So so for models to learn, right, as these traditional models, they didn't make use of any of these unlabeled data, right? But the newer models, the self-supervision that has emerged as a very good practice for these deep learning models. So I'll briefly talk about that also. So, but the idea is, can we use this unlabeled data, which is lying on the internet, right? But the problem is that we don't have the transcripts for them. We don't have the labeling for them, right? But can we use just the audio data to make our models better, right? So that is the main inspiration. And what will it do? It will definitely reduce the fine-tuning requirements, right? And So yeah, so I mean the main goal is to build these systems which can thrive on this unlabeled data and possibly make the fine tuning better, right? So so this is the overall methodology that we have followed for the IndicWav2Vec, right? Where the first part is the data curation pipeline, right? And this data curation pipeline is a general pipeline that anyone can follow for any particular video or audio clip, right? So for our purposes, we have taken this data mainly from YouTube, which I mean just keeping in view the licensing and all. And the second big source for our data was from News on AIR, right, which gave us around $11,000, and the YouTube gave around $6,000 of unlabeled data. So the point, unlabeled is important. We don't have the data that we collected from there. There is no labeling associated. It's completely raw audio only, right, but clean. So the second part is pre-training. I have just highlighted this Wave2Vec architecture, right, which we are using for our IndicWav2Vec models. So this architecture enables us to pre-train the model. And what does it mean to pre-train the model? Is you keep throwing at it the unlabeled data and ask it to learn some representation. So that is the main point. So you keep throwing it the unlabeled data and make the model to learn some representation of the audio. I have some slide for the contrastive task. But yeah, the main idea is you take this data, you feed it to the model, and you ask the model to learn representation. Now that you don't have the labels, but you don't need it for this pre-training, right? You are just making encoder weights to learn something of the representation of that particular language, right? And then when you have this pre-training data, which is, say, for example, in our case, trained for 40 Indian languages, then what you can do is, since the model has seen the taste of these languages, it has seen this waveform, how it looks like, it has seen these amplitude values or maybe the distribution of how data is there in that particular language, then you can take this pre-trained model and then fine-tune it on a labeled data set, right? So now if you have a small, and what we realize we have some results how defining the effect of pre-training. But the thing is that after you have this pre-trained model, you take this pre-trained model and then add a top layer projection or a language specific projection head on top, and then train the model using end-to-end using this labeled data, right? So what it will do, it will help in transfer learning, right? Where you have this pre-trained model which has learned some representation of the audio. When you fine-tune it on a language specific basis, so it will kind of reduce your fine-tuning requirements. It will kind of reduce the number of hours that you require the model to perform better if it was from scratch, right? Then after you fine-tune for a particular language, you have an acoustic model, right? So this basically ends your journey for acoustic modeling, right? But now often what you see is that our fine-tuning models, so they are mostly good for taking up the acoustic features, right? And doesn't care about the semantics of the spoken thing, right? But just to kind of keep things consistent, or just to remove the spelling errors and the mistakes that the model can potentially make, because we are not penalizing it for anything, we are just asking it to learn this acoustic feature mapping, right? So we have this language model which helps in basically mitigating those errors, the spelling mistakes and the sentences, incomplete sentences and all, which is taken care by this language modeling thing, right? So yeah, I'll just briefly touch upon this. So this is how the self-supervision basically looks like. You have this audio which is unlabeled. You don't have a label for it. You have an encoder network. You have a convolutional encoder network which just takes your which basically reduces the temporal dimensionality of this particular audio clip, because given the audio is sampled at 16,000 kilohertz, that means in a particular second there are like 16,000 samples, and you definitely don't want a deep learning model to feed that particular thing. So you reduce the dimensionality by using convolutions. Convolutions are great for extracting features, and then you pass it through a quantizer to kind of make a quantized vectors, right? So which is altogether different task, but yeah, the idea is your quantizer basically gives you the target that you want your model to kind of predict, right? So this is how the self-supervision looks like, but for the brevity, I'll just skip this slide. And then after you pre-train that model, you have some learned representation, and then you take that pre-trained model, add a projection layer, language-specific projection layer, and output the character distribution across whatever the language would be, right? And then on top of that, you just since you have the label data, so you have label for this particular audio clip. You take the you take the sum over all possible alignments, and then just train the model end to end. So this is what ends the acoustic modeling part or ASR part. And as you can see, so I have just two tables. So for our models, as I mentioned, that we took this 17,000 hours of data, which we call Davani, and this is how the effect of pre-training looks like, right? So the blue bars that you can see, these are the models, these are the ASR systems which we have trained right from the scratch, right? We didn't take any unlabeled data. We just took the small fine-tuning data that was there on the internet for these benchmarks, and then just trained them. The second is this red lines, which are definitely, as you can see, are lower than all of them. So they have this pre-trained, they have been fine-tuned on top of the pre-trained model trained on the Davani data set, right? And similarly, we can see the effect of language model, because the model is prone to errors, it can make these grammatical mistakes. Language model is helping all of them. This red color language model is a small language model trained on small amount of corpora, and this yellow color is a language model trained on large corpora. So this is just indicate that how corpus size in language model is helping. So this IndicWav2Vec, so this is in the total highlights that this work has resulted in. So this IndicWav2Vec has resulted in this Davani data set, which is 17,000 hours of pre-training data, and we have open sourced it. Second thing is that we have open sourced our IndicWav2Vec checkpoint, right, which people can use, which people can make their own use of, right? So it's not necessary, so they can take this checkpoint as a backbone and then fine-tune or add task on top of that, right? So why this is important? Because, I mean, just to give you a context, this model particularly took 24 GPUs for 3 days to train. So anyone who would want to kind of build such kind of models may not necessarily need to start from the scratch, right? He can just take the checkpoints, he can just run them on top of it, right? So that is something very useful and definitely very costly. Also, in our work, we have mentioned some of the extensive studies about how language model is helping, what should be the choice of lexicon, and how these language model parameters can be determined, but those are again in the publication. And this work has resulted in a subset of things that we are targeting, right? We are targeting this ASR systems for all 22 languages, but this has just resulted us with state-of-the-art models for 9 Indian languages, 9 languages across 3 data sets, and those ASR systems have their own applications. For example, they can be used in your smart personal assistants. They can be used to kind of convert. They can be also used as a stepping stone for this speech-to-speech translation. While you speak something in your native language, it gets converted into text. Then you have a machine translation engine which just converts it into other language, and then you have a TTS which just speaks that in the native language, right? And we can also have real-time translations. This will form a building block for real-time translations as well. Now, here are some of the future directions that we are working on to make these models better and better. First thing, if I may say that, as I mentioned, that we have this pre-trained model, then we fine-tune it on a particular language, right? So this is again costly, right? Say you have 22 languages, then you will need 22 fine-tunings to get them for every language, right? Now, and this makes the deployment very difficult, right? So you should be having 20 instances of the same 20 instances of the model running across 20 machines or whatever, right? But here, what we are targeting is that we have a single pre-trained model, and we are fine-tuning. We are having a project. We are building a single multilingual model which is capable of transcribing to 22 different languages, right? So, definitely there would be some parameters which would determine which language we are transcribing to, and just firing that particular layer or projection layer. But yeah, so this is something that we are working on. The another thing is that we want, so in the morning meeting, right, it was mentioned that this domain specificity is definitely something very important, right? So if you are building some system for a particular domain, you want it to work perfectly in that domain and not necessarily outside, right? So for those domain specific items, we are trying what are called these adapters, right? Adapters are lightweight parameters, or I would say a small number of parameters that are added to these fine-tuned models, right? And not necessary, and not changing the weights of these fine-tuned models, but changing the weights of these adapters, right? To adapt them to particular tasks, right? So that is something that we are doing, and also we are kind of standardizing these fine-tuned models, right? Because it may be the case that your model is predicting 1 or your model is predicting 8, right? So this is in some way or the other an ambiguous thing. So we are kind of kind of standardizing these things. So how the ASR model should output and all these things. And lastly, we are also building these benchmarks, right, which is very important. If you want to progress upon these model building and all, we need to have some threshold. We need to have some platform where we can say that, okay, yeah, we are doing better and this and that. So yeah, so we are also building these benchmarks.